Hi everybody and welcome back. This example comes from our chapter 7 on friction and inclined planes. And while it doesn't involve an inclined plane per se, it certainly does involve friction. So let's take a look at the problem and see if we can make some sense of it. We've got a 49 kilogram rock climber, and she's performing a chimney climb. I guess that's the technical name for it, between two vertical rock slabs. So I guess this is where you see somebody climb up between two walls or shimmy up. That's what she's doing. The coefficient of static friction between her shoes and the rock is 1.2. Between her back and the rock is 0.8. And I think that stands to reason because it makes sense that her shoes would probably have more grip than her back, which has cloth on it. So the bottoms of her shoes are probably more grippy. So the question is, what is the minimum force that she needs to push on the rock with so that she does not slip? So the nice thing about this kind of problem, being a statics problem, that is her system is static, it's not moving, is that we can assume that the net force on her system is 0, right? Because she is in fact not moving. So we can make that our assumption, and so we can solve for the force required that she needs to push on her wall with to create the forces that'll support her. All right, but we can also write that like net force in the y direction is 0. That's a global statement, but we can also write that as a series of component forces, right, acting all together. So what are some of the component forces acting up to create the net force acting on her? Well, of course, we have her weight force, mg, and that's directed straight down. But of course, there has to be something balancing this out, and you'll notice there's nothing actually underneath her supporting her, but what is actually creating the upwards force to support her? Well, that is the friction forces on both sides of her. So I have the friction, we'll call it the static friction force on the left hand side. The lower subscript s is for shoes, and on the right hand side the static friction force, the b is for her back. So we have those two forces acting in concert with each other to balance out her weight force. We are given the coefficients of static friction for each of those, 1.2 and 0.8, but we don't really want to use these numbers quite just yet, these values. We do want to use the coefficient of static friction, but we know that's used in conjunction with something else to create the friction force, right? The static friction force, and that is the coefficient of static friction is multiplied by the normal force to create the friction force. All right, so the harder she pushes against the wall, the more friction there is made. Well, we want to solve it just for the very minimum that she needs to push. Okay? So the pushing against the wall is really creating that normal force right there. Her back is pushing against the wall, and her feet are pushing against the wall. And really, it's that normal force that we're solving for. If you want to think of it a different way, you can also think of that normal force as being kind of like a contact force between her back and the wall and between her shoes and the wall. And having done contact force problems before, contact forces they're not really external forces, but they're forces that are internal to a system. And what is true about contact forces is that they are equal in both directions. It's kind of like a pair of forces. In other words, she can't push harder with her back than she is with her feet. The pressure between her back and the wall and her feet and the wall must be the same thing. So the normal force can be thought of as this contact force, but since the contact forces are the same in both directions, we can just drop those subscripts right there, back and wall, and just call it the contact force. All right, the contact force, the normal force, it's the same thing, but the key here is that the contact force is going to be equal in both directions. If you can't push harder in one direction than the other, it has to be the equal force on both sides. Okay? So let's look though at the forces that are being added together to keep her from falling. All right? Well, what forces are acting upwards? It's that static friction force from her shoes plus also the static friction force from her back, right? So we have FSS plus FSB. Of course, acting downwards, acting against these friction forces, is her weight. Or actually, I should say her weight is acting downwards. The friction forces are acting against her weight, acting upwards. But we tend to think of up as positive. And so this statement right here sums up all the component forces acting on our chimney climber. All right, so we have these static friction forces being added together. We'll look over on the far right and the far left. We have a more accurate, more detailed description of a static friction force. So why don't we take the coefficient of static friction times the contact force and just drop that in and substitute those in to our statement right there for the component forces. All right. So we have now two pretty detailed, well, one very detailed net force statement. The other net force statement is just 0, right, because she's not accelerating. But either way, these are two statements for net force. And what can we do with two statements for net force? We can set them equal to each other because net force, because both of these are statements for the net force. All right, now remember, what are we solving for? Well, we're actually solving for that contact force, or if you want to think about it this way, the normal force between both sides of our body and the wall. So let's work on isolating that contact force between her and the wall, between her shoes and the wall and the back and her back and the wall. All right, so first thing I want to do is I want to get rid of everything else because this is our working equation right here. All right, so let's move that mg, her weight force, let's move that to the other side of the equation because we want to start getting everything away from our contact force. And now we have these two statements, both of which are added together, but they're multiplied with a contact force. So how do we pull that contact force out? We can factor it out. Let's go ahead and do that. So that comes out in front of the parentheses right there. So we have a contact force times those two added together coefficients of static friction in the parentheses. So let's just divide by everything in the parentheses right there, and that comes down to the other side of the equation. Now we actually have our statement for solving for the forces she has to apply. One thing to remember is that this force, whatever it is, has to be applied by her back and the wall and her feet in the wall. But the key that we mentioned earlier on was the fact that these are both the same force. So let's find out what that force is. Let's go ahead and substitute in our knowns. Our mass is 49 kilograms. Our g, acceleration of gravity, of course, is 9.81 meters per second squared. And then in the denominator, we have our sum of the coefficients of static friction, 1.2 plus 0.8. So what do we get? The contact force between her and the wall is 240 newtons. Once again, it should be pointed out that this is between her back and the wall and between her feet and the wall. But you can't have a contact force without having a pair of forces. And so this force is exerted in both directions by her against the wall to create the proper friction force to keep her suspended. All right, so there you go. That's our answer to that example. And if you have any questions, please make sure you contact me and we'll sort it out. Thanks for watching.